Hi guys, do you hear me?
Yes, I can hear you.
Okay, great. So am I supposed to speak English? I thought somebody told me that it should be in English. Okay, anyway, cool. So as far as I understand, this part is is within a research seminar. Yeah, you call it what? NIS. And so what I'm going to do in this course part, module, whatever the name you use, it will be, okay, first of all, it will be about modern semantic technologies, and it will be more about practical aspects than theoretical. So the plan is like this, that I'm not going to prove theorems. I'm going to show you certain technologies, that is languages and the software you can use for these languages. The languages will be primarily for data and knowledge representation and for formulating queries and answering queries. Yeah, so and all of your tasks, you will have a couple of tests, and the tasks will be very concrete. Yeah, I'll give you a certain context and I will ask you to represent the information, data, and knowledge within this context, and write queries and find answers. These are the problems we are going to consider. So 30, 40 years ago, the main and maybe the only languages for these purposes were the languages of databases. Yeah, how to create databases, tables, constraints, and formulate queries. By the way, did you have a course on databases at all? Can you write in the chat?
Yes.
You did have. So you are saying that you know pretty well how to deal with databases and how to use SQL queries, for example. That, of course, cool, you will teach me. All right, because in some sense, well, at least in the first 4 or 5 lectures, the languages we are going to consider can be regarded as a poor man's databases. So that will be way easier than relational databases. Okay, so there are 2 important things here on the first page. The first is my email address, Gmail. And the second is the site where you can find the slides, some notes I provide for this course. Yeah, let me click it. So this is the website. Now I kept, so today the material, oh, just a second, the material is under 1 and 2. Yeah, the lecture slides I modified and put there yesterday. All the other slides, exercises, and whatever we have there, it's from the last year. Some of this material I'm going to reuse, but expect some changes, and the syllabus will also change a bit. So the task for today is this. Oh no, wait a second. So what else you can find? There are books. Say here I mentioned these 3 books, but I suspect they contain a lot of theoretical, at least the first 2, they contain a lot of theoretical material, which I'm not going to use. Yeah, basically what I recommend is follow the slides and you will have all the information you need. And if not, Google. Yeah, so there are lots of web resources in Wikipedia and elsewhere. There are tutorials, presentations, and so on and so forth. Or ask me if there are problems. Okay, so a better probably the title for this part is the Introduction to the Semantic Technologies, or an Introduction to Semantic Technologies. Although the semantic technologies started with the semantic web idea. So I'll begin by, I think I need about maybe less than an hour just to give you a very shallow introduction to what we are going to consider. And then another hour, we'll have a look at one pretty well-known and old language, which is used in semantic technologies as a kind of language for information exchange. So I don't think that the material of today's lecture is challenging, but you will have 1 or 2 questions about that language. Okay, so historically, yeah, the World Wide Web was invented, if you can use this word, invented by Tim or Sir Tim Berners-Lee a lot of years ago. Why I put these 2 pictures here on this page? Because one could compare the 2 inventions, one by Johannes Gutenberg, long time ago in the 15th century, when he wanted to speed up the printing of Bibles. Yeah, and his idea was to invent a movable type, yeah, for producing books. A very nice aim, and the result, well, by this invention, he changed the society. Yeah, and the society moved to the industrial era. Right? It became an industrial society with knowledge-based economy. Yeah, in the same way, the invention of the World Wide Web by Sir Tim changed the, or is changing our society. Yeah, and as in the case of Gutenberg, the original aim was quite different. Yeah, Berners-Lee worked in CERN, in the European Institute for whatever nuclear physics. Yeah, and his aim was to provide rapid and electronic access to online technical reports, yeah, scientific papers written by the staff at CERN. Yeah, he wasn't thinking about the World Wide Web in those days. Yeah, the aim was absolutely concrete, more so that he was there as a what was his position there? He wasn't a researcher, he was a kind of technical staff there, contractor. Okay, and well, it so happened that this invention changed the society completely, and people say that now we have an information society with digital economy. All right, so interestingly, Tim Berners-Lee recognized nearly immediately that the web he helped construct, it was pretty limited. Although it changed the society, introduced digital economy and so on, still the what this web can do was pretty limited. Yeah, and he came with an idea of a new web, the semantic web, Web 2 or 3. Yeah, where the idea is that computer agents should be able to access the information, the data on the web. Moreover, all the information on the web would be presented as one huge database, so that autonomous computer agents could access this data and do whatever required, whatever is required by users. So the semantic web, this is the term he suggested, Sir Tim. Yeah, well, I wrote here, is a web of data that facilitates machines to understand the semantic or meaning of information on the web. There is, for quite some time, there is an international consortium called World Wide Web Consortium, or W3C. Yeah, and this organization oversees the development of semantic technologies. Yeah, and if you click on this link, you will see what activities they have there. I just wanted to mention that 5 years ago, they changed the name from semantic web to web of data. Now, this is the new term. Anyway, all of this are semantic technologies. All right, so what is the problem with the current web? For us, normally the web is great. So I'll use a simple example to illustrate what was the point of the semantic web and semantic technologies. Now, let's consider the following task. Yeah, so you don't, suppose you don't know me, I don't know myself, so I have a couple of questions, like, where does he, that is me, work? Yeah, what is his research area? Did he publish a book? What his academic position, and so on and so forth. All standard information. How to solve this problem? Easy. Google it. Yeah, so we Google it. The only difficult thing is to spell my name, especially in English. Yeah, and we'll find a web page where there is some information. Yeah, and we as human beings, we read, okay, name, family name, probably position, then address, okay, cool, and then what research, there are some links, there are some books, okay, we are ready to answer the queries. Yeah, so this page contains enough information so that we can answer. So this guy probably works here. This is a book he published. Probably this is his academic position, and so on. Okay, so for us, for people, this is not a big deal to answer these queries. Now, in the web page contains, of course, the information. Yeah, but now imagine that you want to write a program which would extract, which should extract answers to such queries automatically. Can you write an SQL query? Hardly, yeah, because the information here is not structured. It's not a database, it's just some plain text. Yeah, and we understand it because we know the context. So how can we make this data accessible? How can we make it structural? So if you start thinking about this, then a very simple primitive solution is kind of immediate. Yeah, instead of using plain links like here, we add some extra information. Yeah, metadata. What if we somewhere in this link we write this keywords works at. Well, at least for English-speaking people, that would mean, all right, yeah, this link indicates the place where this guy works. Yeah, and this link probably could be labeled with published by, yeah, because it's a link to the publisher which published this book. Right, so these simple things, if we do it in a standard way, in a machine-readable way, standard means that it's a formal language which is known to everyone. Yeah, machine-readable, yeah, also that it's a formal language that can be processed by machines. Yeah, then if we do it in such a way, then maybe we'll achieve some web of data. And this simple idea under the name of linked data or linked open data has been around for about 10 years or so. Yeah, to make all the important data on the web interlinked in the manner I showed in the previous slide, using some common and easy vocabularies like works, like publish, like other things. And by now, if you Google this linked data, the amount of data on the web connected in this manner is simply huge. And here in the center is what is the DBpedia. Yeah, DBpedia is a kind of formal representation of the data in Wikipedia. Yeah, and there are a lot of other things. Geographical, scientific, music, you name it. So the principles of linked data, how to publish data so that it could be part of this global open network are pretty simple. Use URIs, yeah, uniform resource identifiers, URLs, what we normally call. Use HTTP URIs, yeah, so that people can click people or artificial agents could dereference the names, yeah, and provide useful information about name identifiers, and use standard languages like a resource description framework, like Sparkle, which is a query language for RDF in place of SQL, yeah, and so on. So it's being done. A lot of information is linked like this on the web, so the idea is pretty fruitful, and I'll show you some examples later. Now, let me give you one more example, which shows what kind of data representation we are going to use. Yeah, here, let me start with a simple, no, the problem isn't simple. A very important problem, which is known as data integration. And I use a simple example to explain this problem and one way to solve it. So suppose we have two data sets. The data sets, both of them, are about books. So data set A and data set F. Yeah, and suppose that in the case of A, those who created this data set used relational tables. Yeah, so it's a relational database. So we have in this particular example 3 tables. Let's understand the schema. So what do we have here? ID. And as IDs, what can we use? We use ISBN numbers of books. Yeah, international, what is that? Standard book number, ISBN. Okay, the second column is an ID of authors. Sorry, IDs of authors. And these IDs refer to the next table here. Then title. Titles of books, publisher, and publisher ID refers to this table. Yeah, here is clear. Now about authors, we have name, in this particular case, Amitav Ghosh, and homepage of the author. Yeah, and similar for the publishers. All right, so this is one. And another one is F, probably from French, where the data is represented as an Excel sheet. Now the structure is completely different. So what do we have here? ID, and it refers to an ID, but if you look further, then it will be probably an ISBN of the translated version into French. Yeah, so we have here the title in French, and then we have a reference to the translator. So well, French isn't my even worse than English. And then original. Yeah, and here we have the same ISBN number as there. Further, we have ID of the original, then auteur, author, nom, the name, and 13 is probably the name of the traducteur, whatever. Now, this is the data, and I have a query. What is the title of the original? Yeah, and I want this query to be formal, and I want my computer to answer this query. Right, okay, so whatever technology you use, it won't find any answer. Simply because this data sets aren't integrated. Yeah, they are in different formats, they use different languages, no way of answering this query. So, can we do something? One idea would be to find some intermediate representation of the data used in these data sets. Yeah, it doesn't probably have to be constructed physically. Yeah, let's just think of some natural representation of the data, common representation of the data in this data set. Something like this. Okay, so how can we glue this data together? What is in common? Right, so in common is this number, ISBN number of a book. This particular book, The Glass Palace. All right, and then, okay, we found something common, in common. Then I start drawing a picture. Right, it's deep, I have created a node, and I give this node a name, and the name will be this whatever universal research identifier. Right, and then what? No, tables are too difficult to draw. How about the following? What if I started with a node of a graph? It will be a label graph, and then I draw an arrow. And on this arrow, I'll write author. Right, so it will refer to an author. Okay, and to say that it refers to the author according to dataset A, I add some prefix, A:author. It's a namespace referring to dataset A. All right, and where does it go? Where is the author? It goes to this ID. And then from this ID, it's here, I draw another arrow and write A.name. Right, and here it will be this Amitav. Another arrow, and I write home page. And here I write the URL. And I keep doing this. On the other hand, I start from here and draw some other arrow, F, data set F, and write traducteur there, and titre, and so on. Now, by doing this, I represent the very same information in a pretty intuitive way. Actually, here is the full picture. So the French part is denoted or painted in blue. The American part is painted in pink. And the node where I merge, where I have the same URI in the data sets, well, it's pinkish and bluish. Right, so basically I've done nothing substantial, just represented tables as labeled graphs, okay, directed graphs. And I merged two nodes that had the same label. And miraculously, now I can answer the query. Give me the title of the original. So this is the original, this is the title. I just go like this and return Glass Palace. I've integrated the information, the data. But that's just the beginning. In fact, I can do a lot of other things. For example, as a human being, I know that author and auteur are the same things, one in English, another in French. Yeah, so I can say that like author is the same, yeah, equivalent to auteur. Yeah, and I can do other things. Yeah, so the data representation on the previous page can be constructed by the machine. It doesn't have to be physical. The machine doesn't have to materialize this data. Yeah, it can be kind of virtual. I can say that these two concepts, author and auteur, are the same. And I know that an author can only be, well, at least in our world, can only be a person. Yeah, if you read Pelevin, probably you should change this thing. But if it's a person, then a person actually should have some other things like a home page, and probably one person should be determined by a single home page, probably address and other things. Yeah, and actually a lot of people have already introduced a vocabularies to describe people. Yeah, say people's data on social networks. Yeah, by doing all these things, I can find answers to more complex queries. For example, this one, give me the home page of the original author. Now let's see. Give me the home page of the original author. This is original, this is author, and this is the home page. Yeah, this is my query or query pattern. Yeah, so the answer would be this. Now, this is one natural and simple way of representing data, not only on the web. Yeah, here we used different data sets. Well, in my example, it was somewhere on the web. They had different formats. Yeah, MySQL, Excel, could be something else. We could combine the data because we found some identical URIs. Yeah, and we could add some simple extra information, yeah, by using some common terminologies produced by the web community. So this is our aim, in fact, to look through the available modern semantic technologies, yeah, which are or can be thought as a collection of standard technologies to realize this web of data. Yeah, what is included? Formal, machine readable and understandable languages to describe, query, etc., the data and the connections between the data. Yeah, we need formal rules using which the machines can extract information. Yeah, we need the tools that would support this. Yeah, and we need these little ontologies. Yeah, that could say that, I don't know, every person has a web page, author is the same as author, and so on. Yeah, and basically these are the questions I'm going to consider in this part, in my part of this course. Yeah, so I'll show you some formal languages, and I'll show you some tools, and we'll practice with creating formal ontologies. Okay, let me start with semantics. Yeah, semantic technologies. Semantics, what is semantics? Of course, you know that semantics refers to meaning. That's good. Yeah, semantics refers to meaning. That is assigned to symbols. Meaning what? How to assign meaning to a symbol. What kind of meaning? What does it mean to assign meaning to? Okay. My favorite example is this. So on the picture, you see a pint of ale. Okay, and this should, don't look at this. This is some rubbish food, just the pint of ale. And okay, the task is to explain the meaning of this pint of ale. Any volunteer? What is the original? Original, oh, sorry. Original is the, there is one book which is original and another which is its translation. That's the original that was published in English. So, anybody capable of explaining us the meaning of a pint of ale? It's challenging. Just shout or type. What is a pint of ale? Okay, I can start. I'm saying that, okay, this is for drinking. Or I can say, this is a kind of beer. Yeah, and a pint is, I don't know, some measure. Or rather, no, it's a glass. And the volume of this glass is, well, a pint. So what am I doing? Do I add any meaning? Yeah, I connect this thingy, pint of ale. Now this is pint of ale. I connect it. Okay, it's for drinking. Yeah, it's kind of beer. It's in a glass of that volume. Yeah, so I connect one word with other words. Yeah, this is kind of semantics. All right. Now, well, actually, I have a better answer. I'll just take all of you know that will be difficult to a whatever restaurant and show you that this is ale and this is a pint. But say, how would you explain it to a computer? Yeah, you'll need them some fixed vocabulary, yeah, that is known to the computer, that is known to other people. Okay, let's see what the internet says. Right, so let's read. Ale is a type of beer brewed using a warm fermentation method, Okay, okay, fine. It's a plain text. What if we have a look at another one? Here it was Wikipedia, and here it's DBpedia, Databasepedia. Let me click on it. Here it's nearly the same, but we see some hints of a formal language about, yeah, about ale. And then we have some properties. Yeah, you see here property, and then property value. So we relate ale via some properties to some values, right? And you see that these blue things are links, yeah, hypertext links, which connect ale with other, this web page with other web pages. So this is already a more or less readable representation of some data. Okay, so what's written here? Say here, for of, what is for of? Friend of a friend. So these guys have created some common vocabulary. Is primary topic of, it refers to the Wikipedia. DBP type, something. Okay, so there is some formal language that can describe things like pint of ale to some other things. Yeah, and by doing this, well, we kind of fix some semantics. Yeah, semantics is connecting one thing to other things. Right. The word semantics is Greek. Everything else in this discipline comes from ancient Greeks too. Yeah, for example, ontologies. Ontology, well, at least it started sometime around the 4th century before Christ, probably with Aristotle or people who lived in that area. And ontologies at the very beginning were like this. Yeah, what Aristotle tried to create. He tried to classify what exists into like substance, classified into material and immaterial, which immaterial is spirit, and material can be body, which can be animate and inanimate, minerals, and so on and so forth. Yeah, probably those things were quite primitive, but that was an attempt to have terms for many things on Earth, abstract, imaginary, non-existent, but there are some words, and there is a classification. Yeah, substance covers both material and immaterial, and so on. Right, in computer science, our ontologies will be pretty similar, although we'll be dealing not with everything like the Greeks, but we'll be dealing with some domains of interest. Yeah, and ontologies will contain some vocabulary that describe certain concepts, properties, give names to certain individuals in the domain of interest. Yeah, and well, ontologies give formal specifications of these domains of interest. So basically, these things, how to represent data using graphs, like in the example with books, how to formulate queries to such graphs, how to write ontologies in which languages that could describe things like in terminologies like author, title, say that author and author are equivalent. This will be our task. Yeah, to end this introduction, I'll give you a few examples of very simple ontologies formulated in standard languages. Let me start with schema.org. Yeah, so this is an ontology, a very, very simple ontology that was started by by people working on major search engines, yeah, like Google, Yahoo, Yandex, and so on. And the task was to create and support a common set of schemas that can be used to mark up data on web pages. Yeah, like I marked up what was their works at and published by, yeah, this kind of languages. Yeah, let me show you. Okay, for example, this one. Right, so this is schema.org, and here there is a description of a concept person. As you see, the description is in terms of property and value. A person has address. A person has a birth date. Person has a birthplace. Date is of type, of type date. It's a number, and so on. Nothing fancy. However, that's pretty important, yeah, because if your web browser knows that the links have metadata of this kind, kind fixed by the schema.org, then they can deduce a lot of information from this metadata, yeah, and find answers to queries. Oops. Another thing, which of course you all know, or at least you know the term, are knowledge graph. Yeah, it's a knowledge base used by Google for the same purpose, to enhance its search engine search results. Yeah, knowledge graph is also pretty similar, and you see the name knowledge graph. Yeah, so it probably is a graph that is similar to what I showed you about authors and translators. Yeah, and well, unfortunately, Google doesn't want to publish too many details about their language, but it is a kind of graph that I showed you. Another thing, Wikidata. So there are Wikidata and DBpedia. Yeah, in both these cases, the data is represented, well, as shown in this picture. And although it's not a graph, but in fact, it is a graph. Yeah, it relates a certain thing, say here, Douglas Adams, with certain properties. Yeah, you see, we have property, educated at, and some college. Yeah, so Douglas Adams, educated at, yeah, and this URI of college. Yeah, and so on. Other property here, yeah, and other values. Same idea, maybe different language. Yeah, okay, sorry. Yeah, there is a DBpedia version. What else I wanted to show you? Ontologies and sciences. Okay, we'll see this ontology later. So here my example is, I took it from a huge ontology which is called SNOMED, SNOMED-CT. It's a systematized nomenclature of medicine clinical terms. Yeah, everything about people, the structure of their bodies, diseases, treatments, and so on. Yeah, for example, here I took a snippet from this huge ontology about pericardium, which is a tissue and it's contained in heart and so on. It's written in a formal language, which in this particular case is as close to natural language as possible. Okay, so there are other examples further in the slides, but we'll discuss these things later in the module. So the second topic I wanted to discuss today is this. So I formulated more or less precisely the aims of the semantic web and semantic technologies. Yeah, we want to represent various types of data in such a way on the web or elsewhere, in such a way that the data would be queryable, that we could ask formal queries that can be formally answered by computers, not by people who know how to interpret things in this or that context. So this is the task. Now, in order to achieve this task, we need some formal languages which can be used by computers, which can be used by various tools. All right, a language must have an alphabet, and in the case of semantic technologies, the alphabet is very simple. We'll use all the characters which are provided by Unicode, and we will also use URIs. Let me show you. Oops. What these things are. So Unicode is an industrial standard designed to represent roughly all symbols in the world. Yeah, not only Latin, but Russian, Chinese, and you name it. So URIs, Uniform Resource Identifier. Yeah, there are two types of URIs. Actually, nowadays they are called IRIs, internationalized. Yeah, that it's not only just Latin characters, but characters from this Unicode. Anyway, so there are two types of URIs or IRIs. One is a URL, Uniform Resource Locator. Yeah, and this is a typical link like this. And there are uniform resource names. Yeah, the difference is that locator gives you a way to actually access the resource. Yeah, you can click on the link and get to the BBC webpage. Uniform resource name, it just gives an identifier, a unique identifier like this one, like an SBN number. Yeah, but without providing any way of actually getting the resource. So that's easy, and this is how we'll proceed. We'll have things that are written in using some characters, and just sequences of characters will be called literals. Yeah, say names are literals. Michael is a literal. And we also use URIs. URIs will be proper citizens of the semantic technologies. Everything should be either a literal or a URI, yeah, a link to a resource. Okay, now the second ingredient is information exchange. Yeah, now we have an alphabet. Using this alphabet, we can construct some things. Now, the question is, what is the language which can be used for talking about these things? And how our computer agents or people can use this language to exchange information, to get access to information, and so on. So this, in this area, the creators of semantic technologies were pretty conservative, and they decided not to invent anything new, but to use the thing which has been known for a few decades, namely XML. XML, the namespaces in XML schema. And in the remainder of today's lecture, we'll quickly go through examples of XML documents, and I'll emphasize things that you will need to know. We'll also have a very quick look at the query language for XML that is called XPath. Yeah, and we'll see what kind of things can be represented by XML documents. Now, next time will be our first really important language for semantic technologies, which is called RDF, Resource Description Framework, and RDF Schema. Yeah, it will be a little bit more, just a little bit more sophisticated, but the machine representation of RDF documents normally uses this XML. That is why we'll have to take this painful route and look through this horrible syntax of XML. Yeah, and after that, we'll look at the query language for RDF, which is called Sparkle. And after that, we'll deal with ontology vocabularies, ontology languages. Yeah, and we'll have a closer look at the language, which is called OWL, Web Ontology Language, and some tools for creating ontologies and for querying ontologies. Yeah, and then we'll have a very quick look at the mathematics behind all these languages. That's why we have logic here, and we'll consider some description logics. Yeah, so this is our plan. So what is your experience with the XML? All cool. Okay, fine. So you know everything. It's good. Oops. No, it's not good. Anyway, so I'm not going to give you any theory, just a few examples. A little bit. This is a good answer, Yoga. Yeah, a little bit is exactly what we need. Now, this XML or ideas of XML were around, you know, in the basically the middle of the previous century. Because this idea of, look, we have computers, how can we exchange information? Yeah, this was around for quite some time, and it's not a surprise that the first formal language for information exchange was designed at IBM. There were some guys who were working on a project for creating an integrating law office information system. Yeah, there are lawyers, they want to exchange, they work on different parts of some big case, and they want to combine and exchange information. Yeah, so then three guys from IBM created a certain language. They called this language GML, Generalized Markup Language, using the first characters from their names. Yeah, and this language was standardized in the 1980s. Okay, and under the name SGML. Yeah, what was S? I forgot what was this. Standard, GML standard, okay. Now, this GML standard had a lot of applications. One application is the usual HTML. right? HTML was the language which is an application of this SGML. It was used by, designed by Tim Berners-Lee. And the idea is pretty simple. Yeah, we can write things like here, and without knowing the meaning of these things, which are called tags, opening tag, inside of this corners, we have h2 and then /h2. So if you are not familiar with the language, probably you won't understand the meaning. And then what is I, B? Those who know, okay, this is header of whatever level 2, I is for italics, B bold, and so on. Right? But the human reading of this information, of course, is what? We have something, a semantic web primer. There are Antonio and Van Harmelen, the MIT Press. Oh, it's a book. Semantic Web Primer is the title. Antonio is and Van Harmelen authors. MIT Press is the publisher, and then ISBN number. Brilliant, we understand. Yeah, but this language, HTML, was designed not for this. It was designed for showing this text on web pages. Yeah, so this is the human reading. A Semantic Web Primer is a book written by these two guys and published there. The computer reading is this. Yeah, the computer just shows what's written there using certain certain font sizes and certain font types, bold and so on. Yeah, that was the aim of HTML. Just to represent information and nothing else. Yeah, trouble is, of course, that we cannot query such documents. Yeah, and this is the problem with most pre-semantic technologies languages. So HTML documents simply display things and provide links to other documents. And one important thing is that at least in the original version, HTML had a fixed set of tags. You have to learn there, or you need a list of these tags in order to be able to write HTML documents. XML. XML is another application of this GML, and the main difference, or the main first difference, is that the tags are not fixed. But as HTML, XML is also based on tags. Text may be nested, and tags must be closed. That's the most important thing. So this thing, opening tag and closing tag, is called an element. Yeah, so an element starts with an opening tag and ends with the matching closing tag. Yeah, that's nearly it. So XML documents may give some structure to the information. Look at this example. Yeah, I represent the data about that book, A Semantic Web Primer. I represent it in a structural form. You see, I organize all this information within this element, book. And this element contains a few other elements. The first one is title. The second is author. The third is again author, so that I can represent multi-authored books, publisher, and ISBN. So the very important thing is that this document, it has some fancy syntax, opening tag, closing tag, and so on. But if you look at the structure, let us observe immediately that it actually represents or can be represented as a directed graph. This is book. Yeah, this is my element book. And every element book has what? It has title, yeah, an element title, and the element title has some literals, yeah, some name here. Okay, no, name is wrong. What it has? Some characters. Okay, literals. Then book has author, yeah, and then name. Another author, then publisher, yeah, and ISBN. So if we forget about the fancy syntax, so the only thing which is done by this XML document is an organization of certain data in the form of actually it's not a graph, it's a tree. Yeah, unlike my example with authors, this one is a plain directed tree. So this is what we should remember. Okay, no, this is not interesting. Now let's consider a more or less complete XML document. So what does it have? Yeah, this is how it looks like, and this document describes what email. Yeah, and so what is this one? Yeah, this one is a header, kind of prologue, and it refers to the version of the XML and the some encoding of the characters inside. Okay, next is we have elements, and every element, like our head here, has an opening tag and closing tag. Inside the element, there may be other elements. Yeah, of course, there must be some syntactical correctness. Yeah, if we start an element here, then we should add an element before the head element is closed. Right, so there are some syntactical restrictions on this thing. Now, what is this one? Yeah, so far we haven't seen this syntax. Address equals something. Yeah, in fact, this thingy is called an attribute. Yeah, and it's a, you can write it in full like this, address, then closing, and here you write the content. Right, so instead of writing things like this, yeah, so this is an element where there is just one bit of information inside. Yeah, you can instead use an attribute and write address equals something. Yeah, so but formally, attributes are convenient to simplify documents, but strictly speaking, they are not necessary. So we can get rid of them. We have also comments, and that's it, or nearly that's it. Syntactic correctness, well-formed XML documents. Yeah, well, we understand what it is. It's like brackets in arithmetic expressions. Right. So what I wanted to emphasize this one, that the syntax is not part of this modules. I'm not going to ask you to write anything in XML, but I expect you to be able to read and understand what's represented. And what's represented, as I said, can be depicted as a tree. Yeah, so this document, this XML document, can be represented as this tree. So what we have a root, say for example this prologue to the document. Then we have, in this particular case, we have one element email. Then it has the first element head and then body. Head has from, to, and subject. From has name and address. An address has, well, an email address, and so on. So for every XML document, we can draw its tree representation. And the nodes are labeled with the tags. Yeah, so this connection between XML documents and labeled trees is one-to-one. Yeah, you can represent every tree, labeled tree, as an XML document, and the other way around. That's very important. Oh yeah, what I wanted to say is the following, that the order of elements, say this comes first on the left and this comes second on the right. That's important. Yeah, and it is important in particular for the query language, which can be used to extract information from XML documents. Yeah, we'll consider it later today. Okay, so what else is important? Schema. Yeah, so far we had we considered just a very simple language, which can represent information that is of tree shape, or can be structured using this tree shape form. Now, suppose that we want to exchange information. All of us are writing some bits and pieces for a large document that will be obtained by merging all of our bits and pieces. What shall we do then? Then we'll need to agree what kind of tags we use, how these tags are related to each other, what kind of attributes they have, and this is what is known as the XML schema. Yeah, so we want to identify what kind of element and attribute names that we are using, what is the structure, what kind of tree we are using, and so on and so forth. And to represent this information, or it is called schema, there are some special languages. In the former days, the typical language was document type definition, DTD. Yeah, it was in this GML documents. And this was the language for defining the schema, for making agreements like this. And then after that, people created a more convenient, I think, language, which is called XML schema. And this language is based on XML. Yeah, there are some data types. You can define new types and so on. I'll show you a few examples just to be in the picture. Right, so here is an example of XML schema. XML schema is also an XML document, and it describes the format, the valid format of XML data sets, and what elements are allowed and are not allowed, what kind of attributes, the number of occurrences, and so on. Let's have a quick look what's written here, but more or less it should be clear. So what do we have? A prologue, we refer to schema. This is XML namespace. We'll come to this in the context of RDF later. Now, I describe an element with the name email. And what I'm doing now, I'm defining its type. And I say, call it email type. Yeah, and this email type is supposed to describe what can be in the email element. Now let's have a look. What was in the email element? We had what? Email. We had head. We had from, address. We had body. Yeah, this kind of things. And the schema should describe this. So this is where I define my type, complex type, email type. Yeah, so it's what? It's a sequence. And it's a sequence of two things, head and body. And that's it. Yeah, remember the graph. Email has head and body. Head has from, to, and subject. This is what I'm describing. So email type is a sequence of head, and the type of head is head type, and body. The type is body type. It's brilliant and very sophisticated. Now I have to define this and that. Head type. What is a head type? I have from, to, and subject. And moreover, I here say that to, there must be at least one email address, right? Otherwise, nowhere to send. And max occurrences unbounded. Yeah, maybe there may be more than one address. Now, in the case of subject, I define type, and the type is string. Yeah, this is just a string of characters. Yeah, this is what we can do in the XML schema. And after that, okay, so this is a little bit more information about what can be written in the XML schema, but we'll never use it. Using this schema, we can define various, in the schema, we can define various types, which can be, and that's important for you, just a second, let me, yeah. That is important because in our further languages, the data types we are allowed to use come from XML. Yeah, so what we can use in XML, integer, short, byte, long, float, decimal. Okay, the usual stuff. Strings, the usual stuff. Date and time, the usual things. Plus, in XML, we can define more complex data types using sequences, all, a collection of elements and choice one of. I think we'll never use this complex data types, so I just show you some simple examples. So what is here? I have a schema here. Yeah, so I have a complex type, and say I describe a person who is a lecturer. And I describe it by saying that what? That every lecturer must have a name, first name, which is a string. Mean occurrences is 0, so the first name is not necessary. And max occurrence is unbounded. In Russian, normally we need 2. Yeah, Ivan Petrovich. In Spanish, maybe we'll need more, and we don't know how many. So unbounded. And then we need the last name. Right, so it's a sequence of first name and last name, which is a string. Okay, fine. And we also have an attribute, title. Yeah, like lecturer, reader, professor, and so on. Yeah, it's a string, and the use is optional, so you don't have to mention your type. Sorry, your title. Yeah, so this is a one data type I described, and I can extend it without actually changing the schema. Yeah, I add to that schema, I add the following requirements. As a base, I take lecturer type. Yeah, that is, this is my lecturer type, to which I add a few more things, like what? Now, here I add email. Right, so the email address here wasn't mentioned. Yeah, I can simply add the requirement to have an email address without changing this document, but by extending it with this document. Yeah, and I can add some rank here. So when the machine sees these two together, then effectively what happens is that the first document will be extended with more constraints. Okay, that's not that interesting. What is interesting is, oh yeah, namespaces, that's important. Now, when we merge, integrate XML documents, it may happen that in two documents, the same tag is used in for different purposes and in different contexts. In order to prevent name clashes, we use namespaces. Namely, to each name, we add some prefix. And the following example, which describes a, let's see what we have here. We have University of Kentucky, yeah, UKY. And this is the URL for this University of Kentucky XML schema. We have another university, it's called GU, Griffiths University. Kentucky is, of course, in the States. Griffiths University is in Australia, and this is reflected by the two URIs. All right, and now whenever in our, the purpose of this document is to set up a virtual university, which is a kind of combination of Kentucky and Griffith. Right, for the virtual university, I introduce a new namespace, this one, virtual university, and give it also a URI. And now, with each tag in my document, I use this namespace. This refers to the virtual university. This refers to the University of Kentucky. This refers to Griffith University. So, in fact, you can think like this, that if you have something like UKY and then what name, yeah, this in fact is the shorthand for what? Yeah, I have to take this URL, yeah, and copy it here, yeah, and after which I write name if you want. Yeah, so I give totally different names by having unique URIs as a prefix. That's the whole thing, the whole purpose of namespaces. In the context of RDF, this will be everywhere. So you should not forget, whenever you use any name, you shouldn't forget to identify an appropriate namespace. Okay, so I have a few more things to say, not too many. So XML doesn't do anything. Yeah, it's just a way of representing information that can be represented as a labeled tree, nothing else. And if you want to publish this information with their fancy characters, some typesetting structures, then you'll need some extra languages. For example, there is XSL, a family, where is it? Yeah. So XSL has 3 parts, one for formatting XML documents. Another one is a query language for navigating in XML documents. And a third one is for transforming XML documents. In this module, we are interested in representing data and querying data. That's it. So publishing, printing out, typing, that's not interesting. So what I'm going to show you is some examples of using the language XPath. This is a language for navigating or for querying XML documents. You can find a lot of things about this XPath, and what you may need in your future tests or homeworks may be a list of commands you can use. Yeah, in this, all of these commands can be found if you click on one of those links. But the most important, which you can use, will be given in a few pages. All right, so let's see. Suppose we have a document like this. Yeah, what's written there? It's not for normal people. People don't like reading such documents, so I'll quickly draw a graph. So what we have here, we have library, and we have schema, and we have location. Okay, schema, and then location. And it's in Bremen. Or no, that's not good. Location. That's not interesting. What is interesting is that after that we have author up to here, then another author. All right, so then we have author. And we have also a few other authors. On the author, we have what? Name. And name is, this is a literal, it's Borges. Okay, and after name, we have book. And after book, we have title. And after title, we have a literal, the name, the title of the book. Say, this is Labyrinths. Right, okay, now everything's clear. Here we have another book. Title, and so on. Okay, so this is what is represent. This XML document can be huge, but now we understand the structure of data represented by the book. Now, what XPath does? You can write queries like this. Yeah, if you use a proper software and you fix some data like this document, then you can write a query like this or like that. So what do they do? What does this query, say the first one, does? It allows the system to navigate. So what was that? It was library author. Yeah, so we go from library to author. Yeah, and then the answer to this query, yeah, we return the author element, all author elements. And this query says that, okay, first start with library, followed by author. Yeah, so we kind of look at the branches, library, author. This query says find author elements independently on where they are located in the document. Yeah, this double slash means that you don't care which path you have to take to reach this element. Library slash add location. Yeah, what is this? Add stands for the attribute name. So this will return the node that corresponds to the attribute location, which is here. Yeah, what is this? Find all books with which have this attribute bestiario. Yeah, so return then which element? Where is bestiario? Oh, this one. Yeah, so return this element. There are pretty complex things. Yeah, so you can use the square brackets as filters. Yeah, all books with this title. So we'll have some quick exercise next time. I'll show you some software and we'll quickly write some queries. Yeah, on the next page, I gave a list of typical XPath queries. Yeah, or rather constructs that can be used in XPath queries. So we'll have a quick exercise the first thing next time, just to see what kind of things can be asked and answered in terms of XML. Okay, and finally, I wanted to mention a couple of other things about XML to summarize. So XML is a standard language that can represent some structured data. By structured data in XML, we mean data that can be organized according to tree-shaped structure. Now, XML separates the content and the formatting. Yeah, we are not interested about formatting here. Now, XML at the moment is the standard for representation of structured information and is supported by query language. Now, when it was created, the language, the result was that in some sense in big companies it created it caused a data revolution. Yeah, that everything can be structured and shared. Information can be easily passed from those who maintain this information to their bosses, to other branches of companies, and so on. So it was a really big thing. Whether it's suitable for the purposes of semantic technologies is another question. And we'll start with analyzing this thing next time. Finally, I want to mention the following, that because the syntax of XML is pretty awkward for people, there are other variants. For example, you can use the JavaScript object notation as a replacement for XML, for the proper XML syntax. Yeah, and the same concerns JSON schema. Now, this way is much easier, especially for human users. Yeah, for example, here is an XML document in JSON that describes a person. So there are not too many opening, closing things. It's more or less straightforward. First name John, last name Smith, and so on and so forth. Yeah, and you can easily represent this information in the tree form, and so encode into proper XML, and the other way around. Okay, so that's it for today. I wanted just to show you quickly the tasks of semantic technologies and the underlying machine-oriented language for information exchange, that is XML. Next time, after a few examples, we'll move to the first proper semantic technology, which is called resource description framework. Yeah, and I'll explain you a different language where not only trees but arbitrary graphs can be represented. Yeah, it will be next Saturday, same time. Any questions? If you have, yes, shoot, Anton. Yes, you, according to timetable, you have 2 lessons today. I managed to squeeze this 2 in 1 hour and 40 minutes. So all the information I wanted to give you is on the web page, a little bit more detailed than what I said. Yeah, that's it for today. Where can we get the I have no clue where you can get the recordings. Can you please ask, what's his name? Ilya. Okay, as concerns real things. Okay, so you will have a few homeworks. Homeworks will be like this. I'll give, wait a second. Let me go to the, right. So say we go to number 3 and click exercises. All right. So all your homeworks, well, we'll decide when and how you will have your tests, whether it will be a homework, that is, you can do it at home, or it will be an in-class test. Most probably we'll have both this and that. Now, in either case, your questions will be like I show now on this website. Yeah, you will have a few questions like this. Exercise 1. Describe in English the information from the following RDF document given in whatever turtle syntax. Right, you read what is written here and answer, and you will send me a PDF file. In case of a class test, you will write by hand, and your answers will be scanned, and they'll send PDF files to me, which I'll mark. Okay, so you'll have your marks. What was the question? What is the formula of the mark? What do you mean the formula? If you have a perfect answer, you will have 10. If it's a little bit imperfect, then 9, and so on. That's the formula, as usual. Right, so typical questions will be like this. There is a formal document translated into English or Russian, and the other way around. there are English or Russian sentences, like here, the journal article, The Semantic Web Revisited, was written by this and that and published in IEEE Intelligent Systems. Yeah, I'm asking you, please represent this information using this language or that language. Write an XPath query which retrieves all authors' names from this document. Now, these are kind of questions you should expect. Well, later on, there'll be some formal semantics, so there'll be a little bit more mathematical questions. Yes. You'll have something like this. Say, last year, as far as I remember, we had 2 or 3 in-class tests, which were contributing to your mark. Yeah, something like that exactly. Oh, right. I'll type now the link to the slides. Just a second. I'll copy it from here. Okay, so it is okay, try it. This is my home page, / if you Google me, you'll get that home page, then SW15. Probably it's because the first time I gave this course, or a variant of this course, was in 2015. Yeah, and that's it. Then you'll see this page, and all the exercises are examples will be there. So the first serious lecture with really new material and with exercises and so on will be next time. Now, today it was just a brief introduction. More questions? No, today you have no homework. No, for today it's not. As I said, today wasn't serious. It's just a reminder of things that all of you know, or nearly all of you know. Okay, then see you next week, next Sunday. Oh, final exam will be reason. Yes. Okay. Okay, ciao, guys.